Hello everyone. Let's start with a simple question. Have you ever wondered what makes oxygen different from nitrogen or gold different from silver? The answer lies in a fundamental concept called the atomic number. In chemistry, the atomic number, written as Z, is defined as the number of protons present in the nucleus of an atom. Think of it as an atom's fingerprint. It uniquely identifies every element in the periodic table. Here's something even more interesting. In a neutral atom, the number of protons is always equal to the number of electrons. This means the positive charges of the protons are exactly balanced by the negative charges of the electrons, making the atom electrically neutral. Let's make it crystal clear. Atomic number Z equals the number of protons in the nucleus of an atom. If you look at the periodic table, you'll see that it's arranged by increasing atomic number, not by atomic mass. Now, let's explore what makes one atom heavier than another. That's the mass number, denoted as A. Mass number is the total number of protons and neutrons in an atom's nucleus. So, mass number A equals number of protons plus number of neutrons, or in short, A equals Z plus N, where N is the number of neutrons. While neutrons don't affect the atom's chemical properties, they do influence its mass and stability. For example, two atoms of the same element can have different numbers of neutrons. These variations are called isotopes. But what about the electrons? In a neutral atom, the number of electrons always equals the number of protons. This ensures the atom has no overall electric charge. However, if an atom loses electrons, it becomes a positively charged ion called a cation. If it gains electrons, it becomes a negatively charged ion called an anion. Let's take sodium as an example. Sodium's atomic number is 11. A neutral sodium atom has 11 protons and 11 electrons. But when it loses one electron to form a sodium ion, written as Na+, it now has 11 protons and only 10 electrons. Why does this matter? Because the behavior of atoms in chemical reactions is mostly determined by their electrons, especially the ones in the outermost shell, known as valence electrons. Chemists use a smart shorthand to represent atoms and their details, the atomic symbol notation. In this notation, the mass number, A, is written as a superscript and the atomic number, Z, as a subscript, both to the left of the element's symbol. For example, carbon-12 is written as C with 12 as a superscript and 6 as a subscript, 1,2 as superscript, 6 as subscript. See, this tells us everything at a glance. For carbon-12, atomic number 6 means 6 protons, mass number 12 means 12 minus 6 equals 6 neutrons, and if the atom is neutral, it has 6 electrons. Let's do sodium, 2,3 as superscript, 1,1 as subscript. Now, that's sodium with atomic number 11 and mass number 23. Protons, 11. Neutrons, 23 minus 11 equals 12. Electrons, 11 for a neutral atom. This style of notation is used everywhere, from balancing equations to identifying isotopes in nuclear reactions. Let's try a real calculation, step by step. Suppose we have chlorine, shown as 3,5 as superscript, 1,7 as subscript. Cl step 1, the number of protons equals the atomic number, so 17 protons. Step 2, the number of neutrons equals the mass number minus the atomic number, 35 minus 17 equals 18 neutrons. Step 3, for a neutral atom, the number of electrons equals the number of protons, so 17 electrons. So, chlorine atom, 17 protons, 18 neutrons, 17 electrons. You might be asking, why is all this important? Atomic number and mass number are essential for distinguishing isotopes, predicting how elements will react, and understanding the unique behavior of each element. For example, in medicine, special isotopes with the same atomic number but different mass numbers are used in PET scans and cancer treatments. In the world of technology, knowing how many electrons and ions an atom can have is crucial for designing batteries and understanding electricity. The language of chemistry, this atomic notation, allows scientists to communicate clearly whether they're balancing equations in the lab or designing industrial processes. Let's quickly sum up what we've learned about representing atoms. Atomic number Z gives each element its unique identity. It's the count of protons in the nucleus. Mass number A tells us the total number of protons and neutrons. Electrons match protons in neutral atoms and are the key players in chemical reactions. And don't forget that little atomic symbol notation with mass number as superscript and atomic number as subscript is the chemist's shorthand for understanding the invisible architecture of matter. I hope you now see how a simple set of numbers and symbols can explain everything from the air we breathe to the batteries in our phones. Join me next time as we dive deeper into chemical bonding, the next great adventure in atomic structure.